So for the last section of chapter 6, 6.5, we're looking at the resolution of vectors into rectangular components. So we're basically breaking up a vector with a horizontal component and a vertical component to get, let's say, from one side of the vector to the other. So some key ideas: rectangular vector components of, we're just going to call it vector F, let's say, because it will have a force associated with it. So we're taking vector F and breaking it up into two parts, into two components. So these two vectors are perpendicular to each other, and added together, they are going to give you vector F. So kind of like the head to tail method, right? If I were to start here, tail to head, and have this tail starting where the head, this vector ends, and then here the tail to head, then the resultant vector, or my force vector, then would be from the beginning of vector 1 to the end of vector 2, right? Or the tail of the beginning to the head of the second vector. So that's what we're talking about here. And it just so happens that these ones will be perpendicular to each other because I have a horizontal component, like I said, and a vertical component. So vectors that are also perpendicular, and you can see the 90 degrees there, would be rectangular, is where we're getting that from. For a vector F at an angle of theta, if I was standing here and looking at angle theta to the horizontal, right, looking at it for perspective with solving for the horizontal, where I'm using the horizontal side and my vector F side. So I'm not using this side now. How would I calculate that? And that's what's down below here. So in terms of the angle though, the angle is always made in reference to the positive x-axis and then moving in a counterclockwise direction, which I think I mentioned in video 6.4 that's where we are headed, which is why in some of those examples I chose that particular side when I had two triangle choices, why I chose that side of the triangle. So we always are starting from horizontal and moving in a counterclockwise position, okay? So for, we're calling just this the F vector subscript H, just meaning the horizontal portion of vector F. And then this, the F vector subscript V, meaning it's the vertical portion of vector F. So in order to figure out angle theta, angle F subscript H is the horizontal vector component, this component here. So to figure it out, I would need the adjacent side and the hypotenuse side. So SOHCAHTOA, adjacent, and hypotenuse would be cos. That's why we're using cos. So the cos of that angle would be, again, the adjacent first, this side, the horizontal component of vector F over the vector F itself, and we're talking about the magnitudes of them, right? That's why they're in absolute value signs there. So we're getting the magnitude of the force vector, and rearranging it would be to figure out the magnitude of my force vector, the horizontal component, just cross multiplying would be my resultant vector, or my vector F, multiplied by the cos of that angle. And then if I'm looking at the vertical component of my vector F, so this subscript here is the vertical component. So again, just to go back up here first though, if I'm looking at angle theta, right, I need the opposite side with my hypotenuse side. I'm not looking at the horizontal at all. So opposite over hypotenuse. SOHCAHTOA would be S for sine. So that's why I'm using sine of theta to do the opposite side first, which was, right, the vertical vector, over the magnitude of the F vector itself, the hypotenuse one. And then when I cross multiply to isolate for solving for the vertical, the magnitude of the vertical vector, the length of it, right, the force of it, the F vector with respect to the vertical portion would be my F vector magnitude multiplied by the sine of theta. That's just cross multiplying. So what we're doing is we're practicing finding the horizontal and vertical vector components of a single vector. So like I said, we're taking a single vector and breaking it apart into two parts, the horizontal component and the vertical component. And the point of this is hopefully you'll see in the examples that it's actually kind of an easier way to solve these questions than how we've been solving them, let's say just in the last video. So if I can change vectors that are not originally perpendicular into this type of method, then the math is going to be easier. So let's look at these examples. To start with, determine the horizontal and vertical vector components of each force. So again, this is just one force vector, and we're just going to determine what's the horizontal component of that vector and what's the vertical component of that vector. So first I need to draw it. Thought I had a straight line again. And there we go. So I have a magnitude of 560 newtons. So the other thing is I don't really need a scale here. So I don't need to use a scale when I'm using rectangular components. And my angle theta is 21 degrees, but be careful because it's counterclockwise from the horizontal. So again, if this is my horizontal right here, and I'm going counterclockwise, that's to the left, and 21 degrees again, exactly splitting that quadrant in half is 45. So you're basically going almost like a quarter of the way, let's say. So somewhere around there, I'm going to make it just a little bit bigger than it needs to be just in terms of drawing in my angle. So again, this angle here going in this direction is 21 degrees. I have a magnitude of 560 newtons, right? And so what we're trying to figure out is our horizontal component of that vector and what our vertical component is of that vector. So when we are drawing, just to say again, when we're drawing one vector only, the other questions, we had two vectors that we were drawing, right? If I'm drawing one vector only, then I don't need to worry about a scale. So let me try to color code this here. So we have our horizontal component of this vector, which would be from the origin out here. And we can label that as my horizontal, it's supposed to be an H, horizontal portion of vector F. And then we have our vertical component from the bottom up and matching up with the top, the head there of our original vector. And that would be, label it as our F vector, the vertical component, right? The vertical vector and the horizontal vector. Because this is exactly horizontal and this is exactly vertical, we know also that we can put a 90-degree angle in there, which will help us with some math, right? Usually that will make things easier. So it says determine the components. So the components is, again, basically what is the length of the horizontal vector and what is the length of the vertical vector, or the magnitudes, right? Because we're dealing with force. So to find the magnitudes, let's do my horizontal vector first. So I'll do that in orange. So if we go to the formula from up above, the magnitude of the horizontal vector is equal to, go to the formula that was just on the first page for horizontal, the magnitude of my F vector times the cos of theta. Horizontal was cos, right, and vertical was sine. Do I have the force of that vector? I have the force of that vector right here is 560 newtons, so 560 multiplied by the cos of my angle. My angle is 21 because it was from the horizontal up. So that's the correct angle. And then just plug that into your calculator and you should get 522.8 newtons of force for my horizontal vector. And then for my vertical vector, I'll associate that with this green here. Again, write it like the absolute value of the F vector, the vertical component of my F vector, which is the absolute value sign is indicating magnitude. So to figure out the magnitude is the magnitude or force of my actual F vector multiplied by the sine of theta. So again, that force was 560 newtons, the sine of 21 this time. Right, whatever theta is going to be the same. You're just switching it from cos to sine depending on which one you're solving for. And so that answer is, I have 200.7 newtons. And if we take a look, we have the horizontal vector, the number is 523, let's say. The vertical vector is 201, much smaller. And if we can see, this force vector is looks longer, right? The horizontal one looks longer than the vertical one. So it makes sense that the force, right, would be greater for the horizontal than it would be for the vertical. Because we're not talking about equilibrance here, right? So let's try another one. That's it for that one. Now I have a magnitude of 400 newtons at an angle. Theta is 12 degrees, but be careful because it's clockwise from the vertical. So we're not going counterclockwise. So let's make sure we draw that out first. So let's say we are starting 12 degrees clockwise from the vertical. So from the vertical, they're meaning north. So there's my vector, and clockwise, 12 degrees is not very much. Again, I might go a little bit bigger just in terms of to be able to write numbers in there. But really, it should be even probably smaller than that, right? So this is 12 degrees. Let's write that in. And I'll do my best. It's very small, but just listening to what I'm saying, that's 12 degrees in there. And then what else do I know? How do I draw my horizontal and vertical vector? I know that this has a magnitude of 400 newtons. I should write in. And then let's use the same colors. So orange for my horizontal vector, let's say, is going in this direction, and just kind of look at how long you want it to be in terms of to line up to the head of the force vector in red there. And then my green vector coming up, I missed a bottom there and up. I'm a little bit off, but, and again, if this is a horizontal and this is a vertical, then you know that in the corner there we have 90 degrees, which will help. Oh, I'm still in my 90 degrees here. Now let's plug in what we know. I don't have a value for the horizontal vector, so I can just label it horizontal vector. I don't have a value for the vertical vector. That's what it's wanting me to find out. So I can just label it as the vertical vector. Vertical component of F is what that is saying. And what else do I know? I'm just looking here. So I have 12 degrees. I have my vertical, I have my horizontal, I have one side, 400, but this isn't the angle I need. This would be the theta that I need here, right? Let's say. But I can find it. I know that theta would be just simply 90 minus 12, right? So 78 degrees is what we're working with there. So that corner is 78 degrees. And based on that, I can figure out the magnitudes of my horizontal and vertical components of my single vector that I have. So let's do the horizontal in orange. So again, the magnitude of my horizontal vector, same formula, is equal to the force of the original vector times the cos of theta. So the force given to me of that vector was 400 newtons, 400 cos of 78. So 400 cos of 78, I have 83.2 newtons. And then to get the vertical component of my vector, it's equal to the force on the original vector times the sine of theta, right? So again, that force was 400 newtons times sine of the same angle, right? It's always going to be the same if it was 78 here, if it was 78 here. It's just that your sine and cos are changing. So 400 sine of 78 is 391.3 newtons. And again, taking a look, the vertical looks bigger than the horizontal here. The vertical looks bigger, so that number should be larger than that number there. Okay, let's look at example 2. A plane on takeoff has a velocity of 300 kilometers per hour, so there's my magnitude, and at an angle of 10 degrees up from the horizontal. So there's my direction. Calculate the rate at which the plane is climbing and its horizontal speed to 1 decimal place, it's saying. So here I have my, like I was, 1 second. Plane is taking off. Here I have my 300 kilometers per hour there, right? It's my magnitude, and my 10 degrees up from the horizontal is my direction. So then here, when it's talking about, this whole note is about vertical and horizontal components. So what do you think? If this says calculate the rate at which the plane is climbing, the rate at which the plane is climbing would be my vertical component, right? And its horizontal speed kind of tells you right there, the horizontal component. So I have my vertical component and my horizontal component. So what I need to do is draw my vector, right? Again, scale doesn't matter because I'm only drawing a single vector. I'll do it in red. So that's 10 degrees up from the horizontal. So again, if this was my horizontal, we always start in this direction, the positive x-axis, and go counterclockwise. So if it says 10 degrees up, it's just going to be a little bit of a ways up. But again, I can go a little bit higher just in terms of drawing things, but it's really probably like that. Okay, because again, it's not as necessary as it was in the last video to draw things correctly. As you can see, it did get messed up last time. This time it's okay, which is the benefit of why you're learning this. So 300 kilometers per hour. 300 kilometers per hour, I have my 10 degrees up in this direction with my arrow, 10 degrees up from the horizontal, and now I can label my horizontal and vertical components, which are vectors. So I have my horizontal vector, horizontal vector, and I have my vertical, oops, did that again. I have my vertical component there, my vertical component there. So again, horizontal and vertical, I know that that's a 90 that I could draw in there. And do I have my theta angle there? I do. I know it's 10 degrees, so I don't have to calculate anything else. So again, to calculate my horizontal component, the magnitude of the horizontal component is equal to the magnitude of my vector multiplied by the cos of theta. So the magnitude that they give me is 300 kilometers per hour times cos of 10 degrees. 300 times cos of 10, I have 295.4 kilometers per hour. And then to find my vertical component of my f vector, I would take my f vector multiplied by the sine of theta. So the magnitude of my f vector was 300 multiplied by the sine of, again, the same degree, 10 degrees. 300 sine of 10 equals 52.1 kilometers per hour. And that's it for that one.